Now we're going to talk about points of inflection. So this is like the second derivative equivalent of a critical number. What makes the first derivative 0 or undefined is a critical number. What makes the second derivative 0 or undefined is called a point of inflection or inflection point. So let's see what has to happen. A point on the graph of a continuous function f where the tangent line exists and where concavity changes is called a point of inflection or inflection point, and usually I'll abbreviate it as POI, point of inflection. So this is a fancy way of talking here. Let's put the two things that need to happen in order to be an inflection point. So the first thing that needs to happen is it has to make the second derivative 0 or undefined. Make the denominator 0. So just like a critical number, it has to make the first derivative 0 undefined. The point of inflection needs to make the second derivative 0 undefined. But the thing that makes this a little bit more complicated is concavity has to change. So before, if it was always decreasing, if it was decreasing before and after a critical number, that was fine. We just didn't get a relative max or min out of it. But here, if we don't change from concave up to concave down, or vice versa, concave down to concave up, it is no longer called an inflection point. Two things have to happen. It has to make the second derivative 0, and it also has to have concavity change. So to find critical numbers, we're still going to do our same steps. We're going to take the second derivative, we're going to set it equal to 0, we're going to make a sign chart, and we just need to make sure the sign changes to be an inflection point. So let's go back to that example we just did and see, is there an inflection point? Why or why not? So let's go look back at our first answer here. And we have a number that is possibly a point of inflection. We know it qualifies for the first piece. It makes the second derivative 0 at x equals 1. So the second thing, we have to see if that's met. So the first thing, does it make f double prime equal 0? Yes. If you plug in 1, 6 times 1 is 0, or 6 times 1 is 6, minus 6 is 0. But does it do the second thing? Concavity changes. If it does, it's an inflection point. If it doesn't, it's not an inflection point. We still use it on our sign chart, but we don't call it an inflection point. So let's look. Does concavity change? Well, it went from concave down to concave up. So yes, it is an inflection point. So on this graph here, the point kind of in between the two. So we have concave down for this whole piece and then concave up for that whole piece. The point in between where it's switching from down to up is where we would put our point of inflection. So let's add that to our interpretation list. So our point of inflection has an x value of 1. And then to find the y value of it, we would just need to plug into the original function. So to find the y value, I'm doing f of 1. Which is super long function, 1 cubed minus 3 times 1 squared, and then minus 24 times 1 plus 92. The only time you plug into the original is when you want a y value, and unfortunately, because it's an inflection point, you need a y value of it. Point means an x comma y, and I got 66 when I plugged it on my calculator. So that's all of what we would interpret from the second derivative. The first derivative has a little bit more because not only do you find critical numbers and increasing and decreasing, you also interpret relative max and min. Second derivative world is concavity and inflection points. And we just found both, and we're going to do it again. So looking at this next function, we're going to determine where it's concave up and concave down and label any inflection points. So we're going to do it graphically, just like we did with the first derivative. We did some graphs. So let's do that here. So I'm going to label my second derivative on here. So let's remind ourselves, second derivative is concave up and concave down. So concave up is a u, just the left side of the u, or just the right side of the u. Concave down is flipped upside down. Upside down u, just the left side, and just the right side. All are oriented downward. So let's look at this graph. So for this first piece, I'm tracing it And what does that first piece look like it's part of? Does it look like it's part of a U or an upside down U? Because that's going to tell me, is it concave up or is it concave downward? So this one, I would say this looks like an upside down U. So I'm going to call that first piece that I just traced, I'm going to say this is concave down. And then at some point, it looks like I switched from being facing downward to facing upward. This next piece looks kind of like this, which I would say is like having the right side of the U. It looks kind of like that piece there. So I would call this piece concave up. And then my inflection point is where it looks like it's between concavity. It's not really picking a side. It's not part of concave down. Like this couldn't be an inflection point because that's definitely more on the concave down side. So I'm not going to choose that. Here is already looking like it's part of concave up. That looks like a nice U right there, faced upward. So I would say that the point of inflection that's between the two would be kind of right there. Points of inflection are really hard to spot because it's between concavity. It's not really siding with concave down. It's where it's kind of switching from down to up or up to down. Okay, so now let's write this all out nicely. So we're also going to put in the point of inflection. Our point of inflection is 0, 0. So all I'm doing is reading the x value and the y value of that point, and it's right at the origin, so it's 0, 0. And concavity is only going to change at inflection points, just like increasing and decreasing only changed at critical numbers. So before 0, I'm downward. So I'm going to write that interval of concave down as being negative infinity to 0. Before my inflection point, I'm concave down, and after my inflection point, I'm concave up. 0 to infinity. Pretty difficult to spot at first, so let's do another graph. So inflection points are like what's between concavity, and then your intervals, you always want to swap at an inflection point. So let's look at another graph and do the same thing. We're going to find where it's concave up, where it's concave down, and we're going to label the inflection points. So looking at this next graph, I want to figure out, does it look like it's a U or an upside down U? So I'm going to start tracing it and thinking about the shape. Well, the shape, if I draw it off to the side, would you say that looks like a U or is it part of an upside down U? This piece looks like it could be part of this. So we're going to call the first piece of the graph concave up. And I would normally point to these in real life, so it's a little bit of writing on here. You don't have to write everything I write. I'm just trying to narrow down. Normally I'd follow with my finger, and it's not so much messing up with the paper, but I am faced upward at first, part of a right side up U. My next piece that I want to trace switches and looks like it's part of a downward U. It looks like this, if I draw it off to the side, which I connect and could make an upside down U. It wouldn't go into this piece. So the next part of the graph looks like it switches to face down. And then if I continue following the graph and trying to think about when I can make a U, this piece looks like part of a right side up U. So I would say it switches back to being concave up. So what might help the most could be drawing your U's every time. I highly recommended concave up, just the left side, just the right side, and concave down. Whole upside down U, just the left side, just the right side. Because then you can identify what matches what. So this first piece looked like this. I would say it looks like the second way that concave up can look. The next piece was that shape. This looks like the third way that concave down can look. It looks like the right side of an upside down U. This last piece has this shape. Hey, it looks like this part of concave up. So there's a couple different methods. Some of you are going to be very visual and you're like, I don't know why she's saying so much. It's so easy. While others are like, whoa, what's happening? And I'm more on the whoa, what's happening side. I have to go really slow on these. So definitely no shame. So now we can fill out our answers. Well, we know concavity is changing from concave up to concave down to concave up. So we need to put our inflection points in here. We need to figure out where it looks like it's swapping out. And it doesn't have to be perfect on here. It's not the best picture to try to use. Web assign is a little bit more obvious, but I think it's still tricky overall. So this one, I switched from being part of a right side up U to a upside down U. And I need to try to figure out where does that change look like it's happening. So this is definitely a U, and this is definitely an upside down U. So my point in between, I would say, is right at the origin again. So there's my point of inflection. It's where you're switching from one to the other. I switch from being face up to face down. So I have an inflection point. My next piece, I know I switched from face down to face up. So I need to pick a point in between there as well to be my inflection point. And this one's kind of a tricky one. So down to up. I need to pick a point that's like in the middle of the two. So I would go somewhere maybe right in here. This one has like a decimal inflection point. So I'm just going to choose kind of a whole number that looks in between and call it good. I would say about right here is an inflection point where we're swapping between facing down to facing up. So I'm going to label these inflection points. My inflection points, I would say 0, 0. And then my other one, the x value is 2. And the y value, I would say -2. And it might not be perfect because to me, I can't really tell if it's supposed to be a decimal or not, but that's okay. I'm going to call it 2, -2. Somewhere in between. And you could argue that, hey, this is the inflection point. This is where it's in between. It's 1.8, -1.8. And that's fine with me on WebAssign. They make sure it's nice whole numbers. Just trying to give you one really hard example. And if you do this, you can do anything because that's a tricky point of inflection to spot. So there's our inflection points. One thing we did with the first derivative is we did make a sign chart out of them using the critical numbers. So maybe we could do that here if you liked using a sign chart. So I'm going to put my inflection points on here, 0 and 2, make f double prime 0. They're where they're not part of concave down or concave up. They're not negative or positive. Before 0, we said we're concave up. After 0, we said we flipped to being down. So I would say negative, and then after 2, we switch back to being concave up. So whatever helps you. You don't have to make a sign chart, but you certainly could. Remember, only inflection points and infinities are going to go in your answers for these, just like it was only critical numbers and infinities with the first derivative. So for concave up, I would say negative infinity to 0, union 2 to infinity. Remember, negative infinity is to the left, positive infinity is to the right. And then between my two inflection points is where I'm concave down. So between 0 and 2.